Okay, so let's do some more examples with definite integrals. Some more examples with definite integrals. So here we go. We've got the definite integral of 3t squared plus 7 dt from 1 to 3. So first thing we have to do is find the indefinite integral. What's this equation going to be? Well, t squared, these are additive, so you can do this integral, then do this integral. Treat them like two separate problems, okay? The integral of t squared would be t cubed. And then we say, okay, if I take that derivative, it would give me 3t squared. Oh, I have a 3 there. I don't have to do anything to that. That is correct. And then here, the integral of 7 would be 7t. Take that integral, you'd get 7. You're good. Normally, you'd add plus c. We skip that step because this is a definite integral. So we're going to evaluate that from 1 to 3. Okay, so what's that look like? That's going to be 3 cubed plus 7 times 3 minus 1 cubed plus 7 times 1. Okay, well, 3 cubed is 27, right? So 3 times 3 is 9, times 3 is 27, and 7 times 3 is 21, okay? And so that's going to give me 48 minus, and then here 1 cubed is 1, and 7 times 1 is 7, and so that's 48 minus 8, which is 40, okay? Done, 40. So this would be my equation that I'm looking for, and this would be the numerical answer I'm looking for. So those are the two things I need to see. Can you do the indefinite integral, and then can you evaluate that to give me the answer here, okay? Next one up would be e to the 2x, okay? So now, e to the x, the integral is e to the x. E to the 2x is going to be e to the 2x, okay? So literally just going to take that and copy it. Now, if I took that derivative, the derivative of that would be e to the 2x times 2. But I don't have that multiplier here, so I've got to take care of it. So I'm going to put a 1/2, okay? So now when I take that derivative, that'd be e to the 2x times 2 times 1/2 would give me the 1 that I have here, okay? And then that's going to be evaluated from where? -1 to 4, okay? So what's that going to look like? That's going to be 1/2 e to the 2 times 4 minus 1/2 e to the 2 times -1. Okay? Now, what do we know? Well, that's going to be 1/2 e to the 8th minus 1/2 e to the -2. And when we subtract, I don't know why I put 1/8 there, 1/2. When we subtract like bases, right? So e to the 8th minus e to the -2, right? Well, not a lot we can do there, right? We can factor out an e to the something, but really not a lot we can do there, right? So if this was division or multiplication, we could combine those two exponents, but we're pretty much stuck here. This is what we've got, okay? So if you were asked for an exact answer, this is how you'd leave it, okay? We don't want an exact answer. We want an approximate answer. And so I'm going to take the old handy-dandy pocket brain, and I'm going to take 1/2 e to the 8th, okay? 1/2 e to the 8th. I'm going to write that down. That's going to be 1490.479 if I round to 3 decimal places. And then 1/2 times e to the -2 is going to be 0.068. It'll be 0.068 when I round, 0.068. So I'm going to take that 1490.479 minus 0.068, and I get 1,490.411. Okay, so that would be our exact answer. That would be our exact answer, and that would be our approximate answer. Okay, so depending on what you're asked for. Okay, all right. So let's move on to number 7, right? So this is a continuation of the first video on indefinite integrals. Okay, so we've got x plus 1 over x dx from 1 to e. So the first thing we're going to do is break this up, and I'm going to show that. So we're going to break this into the integral of x plus the integral of 1 over x. And these are both dx with respect to x, okay? So in my head, what I'm doing is taking that integral, taking that integral. Well, that integral is going to be x squared, and that'll be times 1/2, because when I take that derivative, it would give me 2x, and I need to get rid of that 2. And then the integral of 1 over x will be ln x, okay, because the derivative of ln x is 1 over x. Okay, cool. And we're going to evaluate that from where? 1 to e. So what's that look like? Well, it's going to be 1/2 e squared plus the natural log of e minus 1/2 times 1 squared plus the natural log of 1. Okay, well, what is the natural log of e? Natural log of e is 1. Okay, and then this is pretty easy. It's 1/2. And the natural log of 1 is 0, right? So that's 1, that's 1/2, that's 0. And this guy would be, if I write it down, would be 1/2 times e squared would be a decimal. This is going to be the only funky one here. This would be 3.695 if I round to 3 decimal places, okay? So then we get 3.695 plus 1 and then minus 1/2, okay? So plus 1 minus 1/2, we get 4.195. Okay? What if they wanted an exact answer? Okay, if they wanted an exact answer, right, this would be this plus 1 minus 1/2. So this would be 1/2 e squared plus 1/2. Okay? Why? Because that 1 minus that 1/2 would give me the 1/2, and we leave that as e squared. So if they wanted an exact answer, it would be here. If they wanted the approximate answer, it would be here. Okay? Let's do one more, number 8 in my examples here. This is 1/2 x squared from a to b. Okay? And so in this case, we don't have numbers, we have letters, and we don't know what those letters represent. So we're going to find this integral. Okay, so the integral of x squared, the first thing you're going to write is x cubed. And then, of course, that derivative would be 3x. Well, I don't have a 3, right? I have a 1/2. So this will be basically 1/6. How do I get that 1/6? Well, it's going to be 1/3 to counter the 3 plus the original 1/2 multiplied together, right? So that 3 and that 3, when I take the derivative, will go away, and I'm left with 1/2 x squared. So that's the 1/6 x cubed, evaluated from where? A to b. What's that look like? Well, that's going to be 1/6 b cubed minus 1/6 a cubed. You can't give an approximate answer for this because I didn't give you numbers to plug in. You have to give an exact answer, and that would be your exact answer. Okay? Nothing else you can do. You could factor out the 1/6 and say b cubed minus a cubed. Okay? That would be your only other option. Both of these are equally good answers. Okay? So let's keep going. If we understand how to find integrals, let's talk about what they mean. So I'm going to zoom in just a little bit here, and I'm going to ask, what does each shaded area represent? What does each shaded area represent? So here on the left, I've got cost per day, time in days. And we took the integral of this function, and it gave us this shaded region. It gave us some value, for that shaded region, some numerical value, 10, 20, 50, I have no idea. But we now have this numerical value. What does that numerical value mean? Well, if this is cost per day, and you take the integral with respect to days, then this is the total cost over t days. Okay, so the example I would give you is if you integrate from 0 to 10, then this is the total cost for those 10 days. Okay, similarly here we've done the same thing. We've got velocity in miles per hour, time in hours, and we've integrated and we got a number, and that number could be 20, 30, 50, 80, it could be a decimal. What does that number, that shaded number, that area represent? Well, this is miles per hour, and you integrated with respect to time. And so this will give you the total miles traveled in t hours. Okay? So let's just say you start driving, time equals 0, and you drive for 10 hours. This area would be the total miles that you've traveled in 10 hours. Okay, so that'd be your odometer reading after 10 hours. Okay, so let's squeeze these other two on here. Okay, here we've got the number of kilowatts used per hour and time in hours. And we went from 0 to some time t. What does this area represent? This is the total kilowatts used in t hours. And again, to make this make sense, you want to come up with a number. Okay, so let's say t is 24, just for an example. Okay, 24 hours, right? This is our electrical use over a day. So here's our kilowatt use over an entire day. Okay, that area represents the total number of kilowatts that we used in 24 hours. Okay, so that's what they would bill us for, is our total kilowatt use. Okay, and then this last one here, we've got sales on the tth day and time in days. Okay, now let's take this and think about it. Okay, this is like a new business opened at t equals 0, and they've been in business for, I don't know, let's say 30 days, 1 month, right? Just for an example. Okay, so they opened day 0. There's their sales. Day 1, there's their sales. Day 2, there's their sales. Day 10, there's their sales. Day 20, there's their sales. Day 30, there's their sales. So this function value, this y value, if you plug in t equals 30, is their dollar amount of sales on the 30th day. If you plug in 20, it's their dollar amount of sales on the 20th day, etc., etc., etc. The area represents what? The total sales over a 30-day period. Okay, and if they truly started at time equals 0, it'd be their total sales over their first 30 days in business, their first 30 days in business. Okay, if we use t equals 30. If we use t equals t, then it would be their total sales over a period of t days. Okay, so that's very, very useful. It's something I want you to think about, especially when you're working application problems. This has boundless applications in physics and engineering, finance, economics, biology, integration with boundaries, right? Definite integrals have just so many applications that you can use. So if you have questions about it, let me know.